Also, I'm excited to kick off the day. So the first talk will be Mike Jordan, who's a bit hard to introduce. How does one, muster the right gravitas? So Mike Jordan is the Pei Hong Chen Distinguished Professor in the Department of EECS at Berkeley. He, was previously on the faculty at MIT, but, and he's won all kinds of awards. It's hard to name them all. But more than anything else, a lot of us these days are talking about the intersection between statistics and computer science and other areas. And really, Mike has been talking about this for decades. So he's, certainly one of my intellectual heroes in this way. And I'm sure that's true for a lot of you. So I'm very excited to hear what he has to say. And thanks for coming.
Thank you, Ankur. It's a great pleasure to be invited back here. I'm literally back where I kind of grew up intellectually. I was at MIT for a number of years. I was in building E10. I don't know if any of you know where building E10 was. Building E10 was right here, and it got knocked down to make room for this building. So my office was literally right down there. So it's an interesting and odd thought. Yeah, so I love IDSS, and I'm glad to be back, kind of renewing ties here. I have indeed been thinking about computer science meets statistics sort of blend for quite some time, and finally I woke up to the realization there was a missing, you should always think about tripods, and the missing part of it was economics. So that's what the talk is about today. The last 5 years I've spent my life kind of trying to learn to become a partial economist in addition to statistician and computer scientist. All right, so machine learning or AI is the buzzword these days. What people often mean by that is pattern recognition. So that's terminology from the 60s and 70s, Duda and Hart. It was gradient descent on bags of parameters. It was sort of everything we have now except just smaller scale. But conceptually really not that different and still with the same limitations. Okay, so you need typically labels of things, and it's become a commodity, but it's a widely overused commodity. There are other problems in the world besides pattern recognition. All right, and so we're going to focus today on decision making. Just within machine learning, it's already a thing. People work on it a lot here. There's a tradition in LIDS, which has decisions in the title, and sequences of decisions, explanations, multiple simultaneous decisions. That's been key in development statistics in the last couple of decades. But we're going to get into decisions with multiple decision makers and market mechanisms, because that's where you really start to make real world decisions. You always have to think about the context, and the context is usually other decision makers of some kind or scarcity. Okay, so here's your picture of deep learning and pattern recognition. So it is hot. It is talked about a lot. But as we pointed out with Daron Acemoglu, who's here at MIT, it's actually not led to productivity gains of the kind you might expect. So productivity gains were associated with search engines, recommender systems actually, massive productivity gains. And if you look at productivity over the last era, it's not happening yet. Okay, so computer vision systems, they can be used. It's a commodity, but it's not really clear where the productivity is going to come from. And I think one of the problems is that the real problems have to do with decision making. They have to do with consequential decision making in the real world, where lives are at stake or things really matter. And there, the pattern recognition machinery is just not enough. That's what I want to get into today. Okay, so let's just think about a single decision for a moment, but a consequential one. Not is there a bunny in the image or not. All right, so think about going to your doctor in a few years or maybe very soon, and the doctor is going to take all kinds of measurements about your body, maybe 100,000 dimensional feature vector, including part of your genome, sequence it on the spot, and it's going to go into the world's largest neural network, which has been trained on all the world's medical data. Just imagine that. Okay, and so predictions are going to pop out of this box. Okay, and suppose that's, for example, one of the outputs, if it's is the heart attack output, that if that number is over some threshold defined by the data, you're about ready to have a heart attack and you should be looked at. Okay, and so suppose that threshold is 0.7 based on all the data to date, and yours is 0.701. Okay, so what are you going to actually do in that moment? Right? Well, you're not going to treat that as a decision and just go with it. You're going to ask the doctor for some context. You're going to think about it a little bit. First of all, you want to know what uncertainty is, error bar, if you will. And I don't mean just a little Gaussian error bar. I need something really calibrated to all of the uncertainty you have about things like, where did that data come from? How old is that data? Is it stale? What machines was it gathered on relative to me? All the sources of uncertainty, and that's going to be very hard. You have to think about that out loud in the moment. And moreover, you got to think of things you never thought of before. I remember I had asthma as a child, or I remember my parents had heart disease. I didn't talk about that before, but yeah. And you're going to reason in the moment. And so now you realize that neural net did not have all the world's medical data. Okay, because there's lots of things that are relevant in the moment of that actual test that were not relevant before, so they're not in the neural net. Okay, and so that's what reasoning is. It's going back and forth with a doctor and now thinking about counterfactuals. What if I were to exercise more? What if I were to do this? And having a dialogue, and that involves data analysis too, the counterfactual analysis. Okay, all right, so just pure prediction is just so limited, even in a single decision, if it really matters to you. All right, but you never make just one decision in life. I'm making lots of decisions today at different time scales, in the moment, over months, and they're all linked in various ways by the complexity of me, but they're linked to all of you too. And we're linked, kind of conceptually, but we're also linked by the transportation system. We're linked by the medical system. We're linked by all the decisions being made in those systems. Data is being analyzed for COVID. That then leads to treatment that affects everybody else, and so on and so forth in tangled loops. All right, so the real question of AI to me is not how do you put thought in a computer. Okay, we don't have it. We're not going to have it probably in our lifetimes. Real thought, real reasoning. The real question is how do you build societal scale systems, planetary scale systems, that are based on data, people's preferences, multiple decisions, and all the tangles of all that, and they really work. They really respond well. They don't give you nonsense. They don't give you bad performance in the tails, et cetera, et cetera, et cetera. That really is the challenge of the era. So that's an engineering challenge, kind of statistics meets large-scale computer science. Okay? It's not AI in any classical sense. Okay, let me dig in a little further. This is a little thought experiment I've been doing over the years. Consider recommendation systems. You know what they are. They are pattern recognition systems. They find patterns in data and reify them. They aren't decision-making systems. Surely, we all know that. All right? So they'll make recommendations. They become a commodity. They're part of this prediction side. But it doesn't take much to realize how they can lead to troubles. All right? So if you start recommending, say, movies, a la Netflix, and everybody started to use the system, you could easily recommend the same movie to 100,000 people in any given day. I'm sure that happens all the time. Is that a problem? Well, there's no scarcity in the world of movies. You just copy the bits as much as you want. So people didn't even think there could be a problem. Same thing even with books. You can do print on demand and get books out as fast as you want. So you can recommend the same book to 100,000 people and you don't worry about it. All right. What about using recommendation systems for real world things like restaurant recommendations? Okay, and so in fact, most of the apps built for this, the companies built with business models doing this, kind of fail. And part of the problem is that if everybody starts using the app, you create congestion. Okay, and so I've seen this actually, and in China, someone was building apps for restaurants in Shanghai, and everyone was starting to use it, and it would send 10,000 people to the same restaurant. Okay, all right, so now how do you fix that? All right, you could treat that as just a load balancing problem, just a computational I send the right number of people to each place, but which people? Okay, or you could treat it as a statistics problem of estimation or constraints or something, but which constraints? All right, and very quickly you're led to the understanding that this should be economic, that there should be utilities in play here, that people have preferences, and those should come in. There should almost be like an auction of some kind in the moment. Okay, there should be a matching market. All right, this also comes home where you start recommending streets to drivers. There's scarcity. I can't send everybody down the same street, and how do I balance that? Do I decide who gets to go where? No, I should offer them the possibility of going somewhere. Maybe there'll be some kind of matching market. Right? And this seems so simple and obvious, but Silicon Valley just gets this wrong. They sort of assume they will decide for us because they know our browsing history. And they can place ads for us so well, right? So why can't they decide where we should go down, which street we should go on, and which restaurant we should go on? Okay? And so lots of business models are just based on that. Take in huge, massive amounts of data, make really great predictions, and they're so good that they can just do all the top-down economics. Okay? So this would be farcical if it weren't sort of so baked into the mindset. Okay, so the alternative is sort of obvious. We've got to create markets. So we want, for example, a two-way market between consumers and producers. All right, now this is not just microeconomics. It is microeconomics, but it's not just matching markets. We're going to think about this with huge amounts of data coming in and influencing all the preferences. We don't know the preferences a priori. We don't know the distributions of the preferences a priori. So we're kind of out of classical microeconomics. Okay, we're going to have to learn all that on the fly as we go. And moreover, there's going to be 100,000 restaurants. There's no way we can have a preference ordering over them. There's no way we're going to experience even a small fractional subset of them. Okay, so we're going to have to start to use social information. We're going to have to start to use low-rank information. We're going to have to start to really blend in statistics to even something as simple as a recommendation system. All right. So let me just allude to the fact that I really like to do work that is mathematics meets the real world. And in this particular case, I have a really great example. I've been involved in something called United Masters, which is down in Brooklyn. It's really, at this point, I can fairly say, revolutionizing the music industry. It is based on the premise that there should be a two-way market in the music industry. Right now, there's no such thing. Famous musicians, a few of them get plucked out. Their music is streamed everywhere, and they make a huge amount of money. But if you look at the actual data, 95% of the songs being listened to today was music written in the last 6 months, and it's by people you've never heard of. All right, so who are all these people? Well, it's 16-year-old kids who have a laptop of some kind, and they're making good music, and they're uploading it to sites, and that's the stuff that's being streamed, because that's fresh and hot, and it's being listened to by 16-year-olds. The 18-year-olds listen to a completely different set of music, by the way. Okay, it's very, very interesting. And some people listen to Beyonce or Kanye, but very few, relative, or the Beatles. We think that's what everyone listens to. It's not. All right, so you would think that all these makers of music are making a living, okay, and they're not. Okay, so their music goes to SoundCloud, it gets stripped out, strip mined, if you will, by Spotify, and Spotify sends it to the listeners, and then Spotify builds their own business model, which is an artificial business model. It's based on subscriptions or on advertisements, just like the usual playbook. What should it be? Well, it should be something like this, that there should be a dashboard for a musician. At the end of the week, I've been making music, and my music's being listened to by people. I should see a map of the United States, and every time one of my songs is listened to, there should be a dot on the map. I look at that, it's just simple data science. I look at that and I say, oh my goodness, I see I'm popular in Columbus, Ohio. I had no idea, but 10,000 people listen to my music there. All right, so I show that to the venue owners there. I suggest I should come give a show there. They look at the same data and they say, yeah, you're popular here. And moreover, we know who's been listening to your music. We can advertise to them directly. And people show up and I make $20,000. I do that 3 times during the year. There's a living. There's a salary. So simple AI, not fancy at all, just created a salary for not just one person, but about 1 million people. It's so simple and so dumb. And you'd think that Silicon Valley would be full of this, and it's just not. But anyway, Steve Stout is in Brooklyn. He's a friend of mine. He's a major personage in the hip-hop world. He created this company. I'm on the board. I'm actually not even on the scientific board. I'm actually the real board. And it has now 1.5 million musicians signed up. And these are the real kids who are making music. They're on one side of the market. There's a lot of listeners here, but in particular, there's the NBA. If you go to the NBA website, behind the clips, there's music. That's these kids, right? FIFA, AT&T, and so on. So brands on one side, not just people, but brands. So real value is being created, and the kids are making the money. Okay, the business model is 5% to the thing in the middle, and 95% to the musicians. All right, so you could do this with not just music. Well, first of all, you do it in Brazil, you could do it in China, you could do it in India, and I hope people will. It's so obvious. You could do it for art, you could do it for journalism, you could do it, so this has a name. This is the creator economy, and it is a buzzword, but too many academics are not even knowing what that is. That's what we should be working to kind of build the infrastructure for. How do we build such an economy in a healthy way? Okay, so this is now where we start to get into trying to bring machine learning together with economics. So this is a thing that is not new either. Nothing really, in some sense, is new in the talk. David Blackwell, back in the 1950s, was definitely working at this interface. Algorithmic game theory has a flavor of this, although not that much data analysis, much more kind of algorithms meets games. But anyway, relationships among Optimum, Equilibria, and dynamics. Multi-way markets, and when you have to explore to learn your preferences, they aren't given, or the distribution's not given. Recommendations meets markets. Uncertainty quantification, I am going to talk about that a bit. It's really critical to do good uncertainty quantification here, not just classical Gaussian or linear model error bars. Mechanism design with learned preferences. We're going to talk a little, actually, I think I'm not going to get there today. But anyway, I'm very interested in contract theory as a way to drive statistical estimation. And then incentive-aware, all sorts of things. And then when you talk about privacy, fairness, and social good, it can't be just computer science and statistics. It's got to be economics, because fairness has to do with my utilities. You're treating me fairly not by giving me the same thing that you give to Xiao Li. We have different preferences. You give him what he wants and give me what I want, and you have to ask me what we want. Okay, so that's part of economics. All right, so I have an outline here. These are just going to be 4 little vignettes to give you a little flavor of the kind of work we're doing in my group. This has been about 5 years now, so I'm kind of selecting a few that I just thought would be interesting to talk about. And I'll go down to enough technical detail so that those of you who work on these things will probably see how we did it. But the goal is not to be technical. The goal is to kind of show you examples of almost little thought experiments, but which will lead all the way to papers. So all the work I'll talk about today is on archive in one form or another. All right, so I'm going to start with this one with Tiana Zernich and Eric Mazumdar. Tiana's a student with me at Berkeley, and Eric just was a student, went to Caltech this year, on strategic classification. All right, so well-known phenomenon in real life. Economists call this Goodhart's law, which is that if you start measuring things in the real world that people care about, such that they care about the outcome, they will shift their data to get a better outcome. And your data is no longer IAD, no longer unbiased, and you have to think about that. All right, so people might be filling out a health insurance form, and they kind of know what you're looking for, and they want to get a low rate, a good rate. So one of the things they might, so the insurance companies know this, and so they make it hard for you to lie. And so they'll do things like, give me access to your cell phone, do you mind? If you opt in, I'm going to record how much it moves during the day, and that's a surrogate for how much exercise you're getting, and so that's a little hard for you to fake. Well, not really, because someone then builds a device that moves the cell phone around all day long while you sit in the couch. Okay, so is this like terrible thing? Is this cheating? Well, yeah, but that's real life. You have to be, the designer of the system has to think about these things. This is a little picture of kind of Goodhart's law in action. Someone measured the poverty index score. I think this was in Colombia. There was a nice little Gaussian distribution when it was first defined. And 10 years later, it didn't look at all Gaussian, and it had shifted to the left because everyone wanted to look poor, get more benefits. All right, so in general, we're going to have feedback loops in learning. And I'm certainly not the first to say this. We're going to have strategic agents, and we're going to have a decision maker. And the agents are going to be sending data to the decision maker, but it's going to be strategic data. They care about the outcome. And the agent is going to send back, in some sense, a predictive model. Kind of gone the day when the predictive model is completely hidden and you don't say anything about it. You probably going to, by regulatory reasons, going to have to reveal something about what the model has, or at least the method it was used. So let's assume we're going to reveal something, and then we're going to have a game. We have an adaptation back and forth, and this is going to be a repeated game. Okay, so now we don't ask what's the optimum, we ask what's the equilibrium, because we're going to be economists. All right, so in particular, this is sort of a 5-year-old topic. And it has been formalized as a Stackelberg game. So you all know what Nash equilibria are. There were 2 simultaneous decision makers choose an action and you get a payoff. Stackelberg is which there's an order. One decision first, and then the other one follows. Now, because it's game theory, the person who made the first decision is looking ahead to think about what the second person will do in reaction and thinking about that. And so it's not obvious whether there's a benefit to going first or second. And in fact, it's different in different Stackelberg games. All right, so we're going to model it this way, and we're going to specifically, it's a specific form of Stackelberg game. It's one in which we're doing statistics inside. It's not just an arbitrary game. It's one in which there's a statistical model being built, say, with something like logistic regression. All right, so we're going to analyze equilibria under modeling, which might be logistic regression. Okay, so in step 1, the decision maker announces a model, maybe revealing the parameters of the logistic regression, or maybe something else. Then the strategic agents are going to send data back, okay? Now, if it's like a credit scoring system, people are going to want to take actions to improve their credit score. So we need to analyze the dynamics now. And the way this has been analyzed is just basically a synchronous dynamics, which goes forward in time, data, model, data, model, data, model. All right, what we've been looking at, which has turned out to be very productive, is to realize that the dynamics will probably not be synchronous. Okay, that there's no reason the decision makers and the data providers are operating on the same time scale, and that even may be a strategic choice itself. Who goes faster? All right, and in fact, if you look in real life examples of this, we're going to call these proactive and reactive. So the proactive one is going to be where the decision maker is slow relative to the agents. Okay, so the agents are providing lots and lots of data, and then occasionally the decision maker updates the model. Why would you ever do this if you're this powerful, powerful decision maker? Well, think about college admissions, right? You're not going to update the admissions model after every student has applied, right? Why? Well, that's just not good economic, it doesn't make any sense. The agents need to have something stable. Okay, that's why prices tend to stay stable. People need to be able to plan and think, and so they do. And there's many other examples where this is kind of the preferred model for kind of social welfare reasons and revenue reasons. All right, but there is the other model, which is that decision makers are fast relative to the agents. The decision maker has a lot of power. They update the model immediately, and of course, this is real life too. So this is what IT platforms do. Okay. All right, so now we have a range of different kinds of games with different timescales involved. Do you get out different equilibria in these games? And what do those equilibria look like? All right. Okay, so we have written a paper where we prove some theorems. The first theorem is that you do get actually different equilibria. You get equilibria in these two different orders, and they are different equilibria. Okay, good. But the more interesting thing, which I find really quite fascinating, is that when this is a statistics game, that you're building, say, a logistic regression, it turns out that both players prefer the equilibrium where the strategic agents lead and the decision makers follow. Okay? The slow one, the proactive one. Okay? So that's interesting. So first of all, it was actually known already, empirically, that the other equilibrium, where the decision maker is really, really fast, that's bad for the agents. They have bad welfare. That was a known problem, right? So you turn it around, and it turns out that strategic agents are happier in this situation where they are the ones that are faster. Okay, maybe that's not such a surprise, but surprisingly, the decision maker is also happier. Okay, this is a theorem. All right, so that's not true of an arbitrary Stackelberg game, but it is true of these statistical games, and there are sufficient conditions of what I mean by statistical here for this phenomenon to arise. All right, so in some sense, this is a theorem in game theory. It's kind of a new theorem. For a special class of games, there's different kinds of equilibria with different properties. But I would argue this is a good example of blending statistics and game theory. It really is core that this is a statistics problem. Okay, so that was vignette number one. So for my later vignettes, I'm really going to need to lean into having uncertainty quantification. All right, so kind of in some sense, the problem with machine learning is it doesn't do hardly any uncertainty quantification. It gives you takes an input, maps it to an output, and that's it. It's a prediction. It's point prediction. All right, in real life, you need some notion of uncertainty for all kinds of reasons, my medical examples, but many, many others. Also to guide further exploration and so on. All right, and this is still an open problem. So you could do the bootstrap if you want. That's going to probably be, at the large data sets we have, too slow. You could do asymptotics and put Gaussians on there, but no one's really going to believe you there. You could be Bayesian, but in the context of these non-parametric neural net kind of things, no one believes your prior and doesn't have any reason to believe the posterior. So it is an open still issue. All right, so I'm going to briefly allude to this line of research that 4 or 5 groups around the world are really working very hard on right now, including mine at Berkeley. And Emmanuel Candes, my colleague at Stanford, has a group that's actively involved in this. It's called conformal prediction. So it goes back to Vladimir Foch, who worked in London and still works in London, a student, I believe, of Kolmogorov, and did this work on conformal prediction just sort of all off on the side. All right, and it was picked up on by some colleagues at CMU, Jing Lei and Larry Wasserman and others. Anyway, with my colleagues Anastasios and Stephen at Berkeley, and then Liwa, who is at Stanford, we've been working on this. All right, so let me just briefly let you know, this is almost an advertisement. I want, especially if there's any econometricians in the audience, I think this is a huge future for econometrics. So conformal prediction allows you to give uncertainty quantification And what I mean by that is coverage, statistical coverage. There's some unknown prediction or parameter, and we want to have an interval or some object. It doesn't even have to be an interval. It could be a set, which covers the unknown truth with an advertised probability, 90% or something. All right, and interestingly, this methodology is completely non-parametric. It's distribution-free, and it can be applied to things like black box predictors because it doesn't need to get inside the box at all. So it's not based on partial derivatives inside the box. It's not based on influence functions. It's not based on bootstrap or perturbations of any kind. It's a calibration layer around the box. All right, so you can have any kind of a box here that has, say, dubious uncertainty quantification. Maybe neural net with one of the ad hoc mechanisms that people use. They're dubious and they probably don't have coverage. Or you could have a Bayesian box that produces some sort of notion of error, but it's dubious because no one believes the prior. Okay? All right, so then we're going to put a layer on top of that, the calibration layer, which uses these ideas of conformal prediction to adjust those quantities into intervals or sets that have actual coverage. All right. So you really need this in all kinds of real-world problems, especially this kind of thing on the right there. We're going to have high-dimensional now uncertainty quantification. Maybe for every pixel in the image, we'd like to be able to say something, or for every object in the scene, what is your uncertainty about that? Okay, so one-dimensional uncertainty quantification, which is often the thing that's studied, is not enough. All right, so just on one slide, let me give you a little bit of at least the statement of what conformal prediction does, and here are some of the references. Again, it's been a very small number of people worldwide working on this, and it's gone back about 20 years or almost 30. All right, so you have data and you have a prediction set now, not just a point. And we would like to say that with, say, some advertised probability, 90%, the probability that the next, an out-of-sample y is in the prediction set is that advertised probability. All right, so kind of amazingly, this can be done. It can be done exactly in finite samples. This is not asymptotics. There's no asymptotics here. It can be done non-parametrically, any predictive model, and it's distribution-free. Okay? And just briefly, kind of the magic here is a couple of ideas. One of them is working with quantiles. And quantiles are a standardized distribution. The other is some form of exchangeability. Okay? So you don't assume IID, but you do assume that if you were to scramble the data, it doesn't change the distribution. True of lots of situations, but not all. And by the way, there is now work moving beyond exchangeability, including in our group. But before we get there, the problems with this. First of all, the error notion can be wrong. The loss function is limited in this situation. And for high-dimensional outputs, this is really the killer. It's extremely conservative. All right. So here's an example that we've actually done in real life. This is colonoscopy and trying to find tumors. All right, so there actually is a tumor in each of these images. And the teal is places where the algorithm has a false positive. Okay, so it's saying that there's tumors everywhere. And it's pixel-wise, so we have huge numbers of error bars, if you will. Every pixel is associated with an error bar. And you want coverage over that entire set. All right. However, the loss function is a point-wise loss function. All right, so you're really trying to ensure that you cover everything 90%. So 90% of the pixels are actually of the tumor pixels are covered. So to do that, you have to be extremely conservative. So this is kind of a known phenomenon there. We're way over predicting. All right, so we've been working on something which gets around that, and you can see in the middle layer there, that's the outputs of this system. It has a tuning knob here. Which allows you to get nested sets of uncertainty quantification, and then it has a particular way to calibrate that allows you to set this. This is a one-dimensional problem. There's these nested sets depending on this parameter lambda, and you adjust that with a simple kind of martingale argument. Okay, so it's one of these kind of pictures here. There is a lower bound on the, upper bound on the risk. The risk is, in this case, for the original work, was assumed to be monotone. And you find a place where the risk goes below some desired threshold for the last time. Okay, and that sets this lambda parameter, and then that calibrates the T, the uncertainty set. All right, so that was too fast for you to really see anything, but I just want to give you a little bit of the flavor that this exists. It's based on kind of quantiles and setting up sequences of nested distribution based on quantiles, and then setting one parameter to calibrate everything. All right, and it does have guaranteed coverage. Okay, so you can use this for anything, really. So here's an example of using this for AlphaFold. This is a system that outputs protein structures. You've probably heard about it. It's quite successful, but it's not entirely successful, and you'd like to be able to annotate it with uncertainty quantification. On this protein structure, I'm very sure. On this one, I'm not. Just briefly, we're able to do that. We're able to use a more complex loss function here, an L1-based loss, and we have nested sets defined in a particular way, and we're able to do the calibration, and this just entirely works. We're able to annotate the entire output of AlphaFold. All right, and then this one here is a state-of-the-art picture. This is done with Anastasios and Jitendra Malik's group. This is the output of a computer vision system, which is labeling objects in the image. And you can see the point estimates are good, but we're actually labeling there with sets. At that point, we think it's a car, but it might be a truck, and it might be a bicycle. Okay? And that set is guaranteed to cover the true object label with a advertised probability. Okay? So this is state-of-the-art computer vision uncertainty quantification. Okay? So you can sort of just look at it for a moment there. You see backpack and handbag, it's not sure about that. And this is being done in real time on a video. All right, and then here you probably can't see that very well, but yeah. Okay, so we're able to locate distinct objects, segment the objects, and label the object, and in all three cases we're able to do that with statistical guarantees. Okay, so real uncertainty quantification. Okay, so that's now a tool in our toolbox. We're able to do this conformal prediction, and we're using it for all kinds of problems. Go to my website, and you'll see a few papers recently on that, and then pointers to a whole range of other papers. Okay. All right, so one of the areas that we're very interested in assuring uncertainty, not just quantification, but also control of uncertainty, are auctions. So auctions are where we're now really getting into the economics. We're trying to really assess what a person wants, what their value is. So we're going to start talking about problems where there's a hidden value. The person's not going to just tell you the value. You have to set up an incentive system that they're willing to engage with, like an auction. And we're going to want to learn about that value over time. We're not going to assume that we know it for sure. That wouldn't even be an auction. But we're not going to assume we know the distribution, which is the classical Meyerson kind of auction framework. So we're going to instead assume that we're able to gather data. All right, now if you're gathering data, just like back in our strategic classification setting, you have to worry about strategic agents. And in particular, in this auction, you have to worry about some agents just being bad people. They want to ruin the auction for whatever reason. Or they have a reason, which is that they want to ruin the auction for a little while so that someone gets calibrated to that. Then later they can come in and reap a big win. And they may not even know what they're doing. They just know that they want to ruin things. Okay, so robustness is at least as much a problem in the economic world as it is in the classical statistics world, where people have talked about it a lot. Okay, so this is with Wen-Shuo Guo, who's a student with me at Berkeley, and then Manolis, who was a student here with Kostas Askalakis as a postdoc now in Berkeley. All right, so I've already said this a little bit, but we're going to now look at real decision-making and with the real economic incentive compatibility issues in mind. So we want to obtain information about privately held values. And classical theory of this is called Bayesian in economics. Bayesian means you assume you have a prior and everything's averaged over the prior. Okay? It's not really Bayesian as a statistician. Bayesian is that you collect data and you update priors into posteriors. But anyway, that's the language. Now there is a literature on learning auctions from sample data. And this is small again, but really interesting literature. And long story short, you can sort of do it. In fact, you can do it with very limited samples, all the way down to a single sample, get something useful. It's promising, but it's not being rolled out. And one of the issues is it's not robust. So we're going to worry about robustness. All right, so let me just, again, this is going to be just a little vignette. I want to give you a little of the flavor. We design an object we call a robust empirical Meyerson auction. Okay, you all know what auctions are. Meyerson is kind of an optimal auction from the revenue standpoint if you assume the distribution's known. We're going to be empirical, therefore we don't assume it's known, and then we're going to be robust. Okay? So robust in what sense? Well, if you have a true value distribution and then you're within alpha of that in KS distance, Kolmogorov-Smirnov, all right, then we're going to have a revenue guarantee which is off by a factor that depends on alpha. Okay? 1 minus alpha. Now, why Kolmogorov-Smirnov? Well, that kind of allows you to arbitrarily move some of the alpha of the probability mass. Not just move it a little bit, you can move it all the way out to infinity. and we're still going to be robust to that. Okay, so just very briefly here, let's suppose we're going to be in an independent model. We have true valuation distributions for n bidders. That's D star, but we've corrupted them to D tilde for each of the bidders, and we've corrupted them up to a level alpha I for each bidder. So it doesn't have to be just one bad bidder. Everybody could be a little bit bad. All right, and here's the theorem. Maybe just look at one of those two lines. The revenue that we get for the mechanism I'm about ready to tell you about on the next slide is off by a phase within a factor of 1 minus the sum of all the alphas of the optimum that you would get if you had gotten the true distributions. Okay, so there's a kind of a nice gradation performance. Moreover, at the bottom there's a sample complexity bound. So after this number of samples, these guarantees hold. Okay, so this is kind of real statistics meets auction design. All right, and the algorithm is actually quite fun and interesting. So you input these corrupted samples, it forms an empirical distribution. All right, you use that distribution to find one which is dominated by the true distribution with high probability, and that's quite straightforward, just a little bit of statistics there. All right, and then you find the minimal monotone hazard rate, or regular, we have two cases, distribution that dominates. All right, and this is just a bit of convex optimization. So you find a lower convex envelope of a certain piecewise constant function using some machinery out of Meyerson's theory, and then you run the optimal Meyerson auction on this lower bound. Okay, so you convexify the problem in a particular way. You now pretend you're in Meyerson's world, you run that, and that gives us the robust auction. Okay, so it's simple at the end of the day. The algorithm and the analysis supports it. Okay, how am I doing? Yeah, 10 minutes left. All right, so I think this is probably the last one I'll mention of the vignettes. I think I'll skip one, but I'll spend a few moments on this. So this is now we're going to be talking about Equilibria. So again, we're down in the game theory world, and matching markets. So that's the economics context. But we're also going to be talking about bandits. So we're going to bring bandits from the learning or statistics world into contact with matching markets. All right, so we've had a couple of papers on this, and this is the most complete one so far with Mina and Alex, who are students with me at Berkeley. Yixing has been a postdoc. She's now at Michigan, and Jacob's a faculty colleague at Berkeley. All right, now the key here is that we're going to bring in a Lyapunov function. All right, so Lyapunov functions are tools, if you're a dynamical systems person, you use all the time. And to design learning systems, it's often really nice to have a Lyapunov function. And in an economic case, you would like to have a Lyapunov function which both helps you set various parameters inside the mechanism, but also is responsible for stability of the mechanism. Okay? Usually in economics, and my ignorance is still there, but usually you define stability as kind of just a 1 or 0 notion. You're either stable or you're not. Like think about stable marriage theorem. Okay? We'd like to have something which is not that black and white, that it's gray. You're a little bit stable, and therefore we can move back towards stability. Okay, so you need a Lyapunov function for that. All right, so that's what we've been doing here. Okay, so as I started with my talk with, we have these matching platforms, and we want them to find market outcomes that learn from preferences, learn to do, say, a stable match under various people's preferences, give people what they want, but they're learning those preferences simultaneously. Okay, so back to my restaurant example, if I go into Shanghai and I start experiencing restaurants, I start to build up some preferences, and I express those to the system, and it should more preferentially give me the ones I care about in the context of a matching market where it doesn't send everybody the same restaurant. It actually does matching. Okay? Now, I'm a machine learning person. I like to have exploration as well. I don't want to just pick randomly a few restaurants and I'm stuck with them forever. I want to always have some probability of exploring. All right? And so I want to get a good regret bound here in the context of a matching market. Okay, so we're going to do this not just with matching markets. Our earlier work was just matching markets, no transfers. Transfers means there's payments from between the two sides of the market. All right, and so that opens up something more real world, like for example, Uber is a matching market. It matches driver to rider, and it has a transfer. There's a payment being made. And of course, the prices and the payments make the mechanism space much more rich and more real world. So we're going to do this with transfers. And so if you're a microeconomist, you know about the Shapley-Shubick model. We're kind of in that tradition. All right, and we're going to, in this context, the contribution is going to be a novel measure of instability. And I'll give an economic interpretation of that in terms of a subsidy. All right, so let me just kind of lean into this issue a little bit. Again, for the machine learning people in the room, we're very used to designing optima of some loss function. And the algorithms don't extend immediately to equilibria. Gradient descent mechanisms don't, and you have to work pretty hard to get to the world of equilibria. All right, but we want to get there, and we want to design dynamics that arrive at equilibria. And moreover, we'd like to design good dynamics. So there's this terminology, the price of anarchy is the difference or ratio between equilibrium and optimum, and we might like to minimize that, okay, to find something that minimizes the price of anarchy, not just characterize it for a class of problems, but actually minimize it. So again, we have to have something which has a continuous flavor that gives us bad price of anarchy and then good price of anarchy, and we adjust things based on that. All right, so here it is, and this is our novel measure, and I don't wanted to get into details. You can read the paper and get the entire thing. But it's got utilities here, and it's got all possible subsets. So it has a Shapley flavor of we're looking at kind of stability, if you will, in some sense, under all possible subsets. And it's got utilities on the left-hand side in that subset, and it subtracts off utilities plus the transfer. So tau sub A is the transfer from one agent based on one vertex in the graph. Okay, so just looking at that, I could try to explain it. It looks reminiscent of some other quantities like VCG kind of quantities. But the right way to think about this is to take its dual, all right? And if you take its dual, then you'll see in the paper that the dual shows that this is actually the minimum amount that the platform could subsidize to make the system stable. Okay, so the system might not be stable in some configuration, all right? So the platform adds some money into it, and the minimal amount that it can add to make the resulting system stable, that is a quantitative measure of how far you are away from stability. Okay, so you don't see that immediately in this equation, but you do see it immediately in the dual, all right? Okay, so it's not an unfamiliar kind of notion of subsidize, but it's a different usage to build this quantity, which I would call a Lyapunov function. This is now something you can optimize over matchings and over transfers. All right, so we've been doing that. We've designed new low-regret algorithms for learning stable matchings. Okay, so we can have a multi-arm bandit model. I'll show you a picture on the next slide. Where there are now multiple agents solving a bandit problem, and they have conflict among them. So we want to match them, and at the same time we want them to explore. And so this could be guided by that Lyapunov function. Okay. All right. So the earlier project in which this kind of built on was by Lydia, who's a student with me at Berkeley, and Hori is now a postdoc here. On bringing just bandits together with matching markets with no transfers. So, but it's very helpful to see the picture here. Here's kind of the classical multi-arm bandit setting, and we have an agent who's selecting among a number of options. They all have random payoffs, and it wants to explore around and find something which has high payoff and have low regret in doing so. And so it samples something, gets a reward, and then does something like a UCB algorithm to decide what to choose next. All right. Now, if you want to blend this with a matching market, the classical matching market, not Shapley-Shubik, but the kind of stable marriage matching market, we'll have agents on the left and buyers on the left, sellers on the right, and you assume that the preferences are known a priori. Someone wrote down their preferences. So college admissions, I would have to write down for every college which one I prefer, and every college has to write down which, so on. And again, in real life, you often don't know these preferences a priori. No one knows them, including the agent themselves. They have to experience things to be able to do this. All right, so in the original paper, we set this up as just competing agents. We're trying to solve stable marriage with exploration. And we worried about what happened when two agents would pick the same option. This is congestion. Two people arrive at the same restaurant. There's only one seat. And we modeled this by sort of different from networks, congestion networks, that only one of them got the reward. Okay, who gets the reward? Well, maybe the bear gets the reward, and the human gets nothing, and that's because the right-hand side of the market prefers the bear, because the right-hand side has its own preferences, which it may be learning as well. Now, when the human sees that, they realize, oh, I like arm 2, but The bear seems to like arm 2, and when the bear picks it, the bear gets it, I don't, I lose out. So I better explore more than I otherwise would. Okay, so there's going to be an extra regret that you would have to pay because of the presence of other agents. And the question is, how bad is that extra regret? And from the previous paper, we were able to analyze that and show that, in fact, you only lose in a constant. The actual regret is still logarithmic in the number of rounds, but you lose in a constant. This new framework allows us to reanalyze that in a simpler, more transparent way, just using this Lyapunov function. Okay, last couple of minutes before I finish. I want to pop up to the very, very, very top level. Data science, machine learning, AI, all these terminologies. So I'm trying to bring economics into the picture. It's not just one thing here, but in some sense there is something happening right now, which is kind of one thing. So think about chemical engineering in the, say, 30s or 40s. Before that, there was not a field called chemical engineering. But there was chemistry, there were principles, and you could pour test tubes in labs and make things. And quantum mechanics was sort of known, so there was explanations of everything. But the idea of building a factory with thermodynamics at hitherto unthought of scales and flows and all that, that was not obvious. And not just engineering had to be worked out, but mathematics had to be worked out. Right? And people started to build factories, and sometimes they worked, sometimes they just didn't work, and sometimes they exploded, and so on. And eventually a field emerged in parallel with that called chemical engineering. Okay? And it's not just engineering, it's a mathematical field. Same thing with electrical engineering. There was Maxwell's equations before there was electrical engineering. So it was a deep understanding, but to develop ideas like impedance or power or whatever, electrify cities, you had to develop whole new principles, and that's called electrical engineering, right? So I think that's actually what's happening in our era. We have these proto-principles for designing world-spanning systems with data flows and human preferences in the loop. And we're using proto-principles from computer science, algorithms, and from statistics, models and uncertainty. And we're building it together like people built factories in the chemical engineering world, right? Not really knowing what we're doing. Sometimes it works. Uber sort of works, but sometimes it fails, explodes. It has externalities, right? And so, especially for the younger people in the audience, I would argue that's what's happening in our era. Something like chemical engineering is emerging. It's fundamentally a real-world discipline. It's trying to do things in the real world, build systems that really do work and have guarantees, and it's going to need new mathematics. Okay? We're definitely not done. We're only at the beginning. All right? And it's not AI. It's not certainly classical AI. It's not putting thought in a box and assuming that box can be shipped out there and do all these wonderful things. The naivete of that is breathtaking. All right, so then last little picture here. I do think statistics meets computer science, if you want to call that data science or machine learning, is definitely a big part of what's happened in this era, but it's not everything. And in particular, economics has already had pairwise linkages with these fields. So statistics meets economics, maybe simplifying a bit, but that's econometrics, measure the economy, but not so much about mechanisms and algorithms. All right? Statistics meets computer science, that's machine learning. Okay? There's nothing new in machine learning. Okay? It's just deepening some topics that were already existing in statistics and computer science. And then economics meets computer science, that's algorithmic game theory. But very little data and concern with that. All right? And of course, the real thing is that all emerging problems blend all three. And that's not just academically. If you go to a company like, say, Amazon, that does logistics chains and prices and shipping and all that, around the table, there's an economist, a computer science, and a statistician. So academically, I think we need to reflect that. Thank you, Ankur.
We have time for one or two quick questions, and then before we go on to the next topic.
Mike, it's always great to hear your talk. Do you have a name for this fit? So you're the first to name it.
No, I want you to be a name, someone who's clever with names. No, I've tried to name things for like 20 years when all these things were kind of clear they were emerging. And then you give them a name and people would say, no, not that, or they hated being labeled with that or whatever. And it's just, it's a tangle, it's a sociological tangle. So maybe if someone has so I think data science was okay for some part of it for a while. I'm not sure it's necessary, but I think I started to use it because people in industry were using it. They wanted someone with statistics and computer science. They wrote down in their job, data science. I would see that. I'd say, oh yeah, we better have an academic discipline, which reflects that. It's like 20 years ago. But it still hasn't become, my heart doesn't warm to it that much. I mean, with all due apologies to HDSR. But I don't know what it is. And I don't know chemical engineering before that. Who knows what it was called? One should look into the history. Scott, nice to see you.
Yeah, How do law and government figure in
Yeah.
the triangle? Are they a pyramid?
Yeah.
Another
No, I don't want to elaborate on my diagram. I think the tripod is perfect. I want to stay with that. But, but think about chemical engineering. It was not just chemistry and fluid flow. And around it, there was all kinds of things, including environmental science eventually, and law, right? And so any seriously powerful entity, engineering-oriented entity that impacts the real world, had better be talking to the lawyers, the sociologists, the social scientists, the environmental scientists, et cetera, et cetera, et cetera. So any powerful engineering discipline creates a whole new set of problems and challenges for all those people. That doesn't mean they're in the inner loop of designing the system, but it's not that they're excluded either. But I do not like sort of everybody in academia is in data science. I think that's not a helpful thing to do. I think it's an umbrella, but it is also has some targeted problems. And this discipline I'm talking about has some targeted problems, and certainly mathematical algorithmic people got to get after them, but the mathematical algorithmic people had better wake up to all of the externalities and all the constraints. And I think econ just helps a lot, because it definitely brings people into the picture. It's not just about data and algorithms, and it involves incentives and people lying and cheating and et cetera, real stuff. And when you start talking about people lying and cheating, lawyers are not far to be found.